Researchers employed density functional perturbation theory and a mixed basis pseudopotential method to investigate the lattice dynamics, electron-phonon coupling, and superconducting properties of alpha MoB2 under applied pressure. Analysis of phonon modes along high-symmetry paths revealed that those with large phonon line widths significantly contribute to the electron-phonon coupling constant. However, the highest frequency optical phonon modes, dominated by B vibrations, have a marginal impact on the electron-phonon coupling constant. Instead, acoustic low-frequency modes of predominantly MoB character largely controlled the electron-phonon coupling constant. At a pressure of 90 gigapascals, where alpha MoB2 forms, the phonon-mediated pairing enters the strong coupling regime, and the estimated superconducting critical temperature Tc aligns with experimental observations. Further increasing the applied pressure leads to a reduction of Tc, correlated with a hardening of the acoustic low-frequency phonon modes and a decrease of the electron-phonon coupling parameter. The discovery of superconductivity in magnesium boride over 20 years ago sparked a search for new superconducting materials within the family of diborides. Despite extensive research, it was concluded that magnesium boride is already optimized by nature, and attempts to further improve its superconducting properties have been unsuccessful. In contrast, alpha MoB2 exhibits promising superconducting properties under pressure, highlighting the potential for new diboride-based superconductors. The electron-phonon coupling and superconductivity in alpha MoB2, a transition metal diboride, are discussed as functions of pressure. Unlike other similar compounds, alpha MoB2 exhibits unique properties. It becomes superconducting at pressures above 20 gigapascals, with its critical temperature, Tc, increasing rapidly with pressure, reaching 32.4 K at 110 gigapascals. Theoretical calculations suggest that the pairing mechanism differs from that of magnesium boride, involving electronic states of the MoD character and a combination of morelated low-frequency phonon modes with B-dominated ones. This paper presents a comprehensive study on the lattice dynamics, electron-phonon coupling, and superconducting Tc of alpha MoB2 under applied pressure, ranging from 70 gigapascals to 300 gigapascals, utilizing density functional theory and density functional perturbation theory. The computational details of the study on electron-phonon coupling and superconductivity in alpha MoB2 under pressure involve density functional calculations using the mixed basis pseudopotential method with norm-conserving pseudopotentials for MoB, NB, and B. The authors employ a mixed basis scheme combining local functions and plane waves for valence states. Calculations are performed with the PBE form of the GGA exchange correlation functional, utilizing a Monkhorst-Pack special K-point set and Gaussian smearing of 0.25 electron volts. Phonon properties are calculated via density functional perturbation theory as implemented in the MBPP code. Phonon dispersions are obtained by Fourier interpolation of dynamical matrices calculated on a 6 by 6 by 6 Q-point mesh. A denser 36 by 36 by 36 K-point mesh is necessary for the calculation of electron-phonon coupling matrix elements. The Eliashberg function, alpha 2f, omega, is calculated using phonon dispersion and electron-phonon matrix elements. Phonon line widths, gamma q eta, represent the damping of phonons due to their interaction with electrons. Electron-phonon coupling matrix elements, GQ eta K plus Q nu, K nu, are computed, representing the scattering of electrons between different electronic states by phonons. The authors also derive the average Allen-Dines characteristic phonon frequency, omega log, which is an important parameter in the study of superconductivity. Electron-phonon coupling and superconductivity in alpha MoB2 are investigated as a function of pressure. The square average phonon frequency, omega 2, is calculated using the Eliashberg function alpha 2f, omega. The average electron-phonon coupling constant, lambda, is computed, and its frequency-dependent counterpart, lambda, omega, is determined. The Eliashberg gap equations are numerically solved to determine the superconducting critical temperature, Tc. The alpha MoB2 crystal structure is optimized, and its equation of state, E, V, and P, V, is obtained. The optimized C, A parameter is plotted as a function of applied pressure, showing remarkable agreement with experimental data and previous calculations. The frequency-dependent electron-phonon coupling, lambda, omega, is essential for understanding alpha MoB2's superconducting behavior. The Eliashberg function, alpha 2f, omega, is used to determine Tc by solving the Eliashberg gap equations numerically. Electron-phonon coupling and superconductivity in alpha MoB2 under pressure are the focus of this research. Data from Pei et al. At 90 gigapascals reveals a 0.3% difference in volume and a 2.1% difference in the C/A ratio, demonstrating high accuracy through structure optimization calculations using the ELK code. A comparison of electronic band structures and density of states at 70 gigapascals and 120 gigapascals, as shown in Figure 2, reveals modest changes around the Fermi level with a bandwidth increase. The main pressure effects are an increase in bandwidth and a small reduction of states at the Fermi level. Phonon dispersion and density of states for specific pressures highlight the low-frequency region dominated by MoB vibrations, the high-frequency region by B modes, and the frequency gap between them. The main effect of pressure is a generalized hardening of phonon frequencies, affecting the phonon anomaly at the LA path and reducing its strength. This research provides valuable insights into the behavior of alpha MoB2 under pressure, shedding light on its potential as a superconducting material. Electron-phonon coupling and superconductivity in alpha MoB2 are investigated as a function of pressure. Phonon dispersions and phonon density of states, PHDOS, are calculated at selected pressures of 70 gigapascals, 90 gigapascals, 110 gigapascals, and 120 gigapascals. Figure 3 illustrates the phonon dispersions, with vertical red lines representing the electron-phonon coupling constant lambda q eta. The figure labels denote acoustic phonon branches, A1, A2, and A3, and the highest optic branch, OP, at the AHLA paths. Figure 4 visualizes the phonon modes corresponding to the acoustical A3 and optical OP branches at the H and L points. The size and direction of the arrows indicate the vibrational directions and magnitude. For the H-point A3 branch, the related arrows are scaled 4x for visibility. The electron-phonon coupling constant lambda q eta is a critical parameter in understanding alpha MoB2's superconducting properties. Lambda q eta is typically calculated using the Allen-Dines modified Macmillan equation, which accounts for the phonon density of states and electron-phonon coupling strength. The results demonstrate the significant impact of pressure on phonon dispersions and electron-phonon coupling in alpha MoB2, consequently affecting its superconducting properties. These findings provide valuable insights into the underlying mechanisms governing superconductivity in this material, with important implications for designing high-temperature superconductors. Electron-phonon coupling and superconductivity in alpha MoB2 are investigated as a function of pressure. Phonon modes corresponding to the acoustic A3 and optical OP branches at the H and L points of the irreducible Brillouin zone, IBZ, are presented, revealing that A3-related modes are dominated by MO atoms, while OP modes are ruled by B atoms. Linewidths and electron-phonon (EPH) coupling constants for alpha MoB2 at 70 gigapascals and 120 gigapascals along the AHLA paths are shown, highlighting the significant contributions of acoustic phonon branches, A1, A2, and A3, and the highest frequency optical branch, OP. The largest line widths are found for the A3 branch, with a strong peak located at the H point, followed closely by the OP branch. These results indicate an important participation of phonon modes dominated by MO, A3, and B, OP, in the EPH coupling. The EPH coupling constants, however, show a different trend, with the influence of B phonon modes fading away due to the factor 1, omega 2 q eta entering its definition. In contrast, the large EPH coupling constants of the acoustic branch A3 are boosted by the low frequencies of these MO phonon modes, especially around the phonon anomaly close to the L point. With increasing pressure, while the line widths increase slightly, lambda q eta strongly reduces, correlating with the observed hardening of this acoustic branch. The analysis of the evolution of superconducting properties as a function of pressure is facilitated by the calculation of the Eliashberg function alpha 2f, omega, the EPH coupling constant lambda, and the Allen-Dines formula for the critical temperature Tc. The research on alpha MoB2 under varying pressure focuses on electron-phonon coupling and superconductivity. It presents the characteristic phonon frequency omega log and the square average phonon frequency omega 2 for each pressure case. The Eliashberg function alpha 2f, omega, and the frequency-dependent EPH coupling constant lambda, omega, are calculated and shown in Figure 6. The largest contribution comes from the acoustic low-frequency region, dominated by MoB phonon modes along specific paths. The coupling strength, as represented by lambda, is highest near the phase transition at 70 gigapascals and decreases with increasing pressure. Figure 7 shows the evolution of these quantities with pressure, agreeing with reported values at 90 gigapascals with a slight difference attributed to structural parameters or pseudopotential construction. The strong pressure dependence of the coupling is mainly due to low-frequency phonons. Electron-phonon coupling and superconductivity in alpha MoB2 are investigated as a function of pressure. The density of states at the Fermi level, the Allen-Dines characteristic phonon frequency, the square average phonon frequency, and the EPH coupling constant are all calculated. Alpha MoB2 remains in the strong coupling regime until 300 gigapascals, with lambda equals 0.95. These parameters are compared to those of NBB2, revealing differences in coupling strength and superconducting properties. The evolution of Tc as a function of pressure is analyzed using the Allen-Dines equation and its corrected version for strong coupling systems. This research provides insight into the high-pressure behavior of alpha MoB2 and its potential as a high-temperature superconductor. Electron-phonon coupling and superconductivity in alpha MoB2 are investigated as a function of pressure, employing a multifaceted approach. The Allen-Dines equation, its corrected variant, and the numerical solution of the isotropic Eliashberg gap equations are utilized to provide a comprehensive understanding of the superconducting properties of alpha MoB2. A key aspect of this analysis is the comparison with experimental results for alpha MoB2, which reveals significant differences in superconducting temperature estimates between strong coupling schemes and the standard Allen-Dines equation. Notably, in the low-pressure region, alpha MoB2 exhibits strong coupling behavior, leading to discrepancies between the estimates. The Allen-Dines equation, a widely used tool for calculating the superconducting transition temperature, is based on the assumption of weak electron-phonon coupling. However, in the strong coupling regime, this equation underestimates the transition temperature. The corrected Allen-Dines equation and the numerical solution of the isotropic Eliashberg gap equations, which account for strong coupling effects, provide a more accurate description of the superconducting properties of alpha MoB2. By applying these approaches, the study yields a detailed understanding of the pressure-dependent superconducting behavior of alpha MoB2, highlighting the importance of considering strong coupling effects in the analysis. The findings have significant implications for the development of high-temperature superconductors and provide a framework for investigating the superconducting properties of other materials under varying pressure conditions. The study investigates the lattice dynamical properties, electron-phonon coupling, and superconductivity of alpha MoB2 under pressures ranging from 70 gigapascals to 300 gigapascals. It reveals that the electron-phonon interaction leads to significant phonon line widths along specific high-symmetry paths, particularly for the highest frequency optical phonon mode and low-frequency acoustic phonon modes. These modes contribute predominantly to the electron-phonon coupling constant. As pressure increases, the phonon spectrum hardens, especially the acoustic low-frequency phonon modes, and the electron-phonon coupling constant decreases. The density of states at the Fermi level remains relatively unchanged. Estimates for Tc, calculated using the corrected Allen-Dines equation or by solving the Eliashberg gap equations, show a decrease with applied pressure, correlating with phonon hardening and the reduction of lambda. Experimental Tc values agree well with calculated ones at 90 gigapascals and 110 gigapascals, but more data for higher pressures is needed to fully assess Tc trends for alpha MoB2. Electron-phonon coupling and superconductivity in alpha MoB2 are investigated as a function of pressure. Theoretical calculations based on density functional theory and the linear response theory are employed to determine the electron-phonon coupling strength and superconducting transition temperature. The authors find that the electron-phonon coupling strength in alpha MoB2 increases with pressure, leading to an enhancement of the superconducting transition temperature. This is attributed to the increased density of states at the Fermi level and the stiffening of phonon modes under pressure. The calculated superconducting transition temperature as a function of pressure is in good agreement with experimental data, validating the theoretical approach. The results suggest that alpha MoB2 is a promising material for high-pressure superconducting applications. Furthermore, the authors analyze the phonon dispersion and electron-phonon coupling spectra to identify the key phonon modes responsible for the superconductivity. The calculations reveal that the acoustic phonon modes, particularly the longitudinal acoustic mode, play a dominant role in the electron-phonon coupling and superconductivity in alpha MoB2. The study provides valuable insights into the interplay between electron-phonon coupling and superconductivity in alpha MoB2 under pressure, shedding light on the underlying mechanisms that govern its superconducting behavior. The findings have implications for the design of high-pressure superconducting materials and devices. The research paper delves into the electron-phonon coupling and superconductivity in alpha MoB2, examining its properties as a function of pressure. Utilizing theoretical calculations via the quantum espresso package, the study analyzes the electronic structure, phonon dispersion, and electron-phonon coupling of alpha MoB2. It is discovered that the compound exhibits high electron-phonon coupling, which leads to its superconducting properties. The paper also explores the effects of pressure on the material's electronic and phononic properties. Employing the ELK code, a full-potential linear augmented planewave method with local orbitals, FPLAPW plus low, is applied to calculate the electronic band structure and density of states. This reveals that alpha MoB2 has a complex band structure with multiple bands crossing the Fermi level, indicating a multi-band superconductor. Phonon dispersion calculations show that alpha MoB2 exhibits several phonon modes, some of which are soft and contribute significantly to the electron-phonon coupling. The paper highlights the importance of these soft modes in enhancing the material's superconducting transition temperature. The research discusses the effects of pressure on the material's properties. By applying pressure, the electronic band structure changes, leading to variations in the density of states at the Fermi level. This, in turn, affects the electron-phonon coupling and consequently the superconducting properties of alpha MoB2. The paper also compares its findings with previous studies on similar compounds, such as MoB and Mo2b5. It is noted that alpha MoB2 exhibits higher electron-phonon coupling and a higher superconducting transition temperature than these compounds, making it a promising candidate for high-temperature superconductivity applications. In conclusion, the paper presents a comprehensive study of the electron-phonon coupling and superconductivity in alpha MoB2 under pressure. The results suggest that alpha MoB2 could be an important material for future research in high-temperature superconductivity.